Right, hello everybody. So today we're learning about parametric equations. So our motivation here is that usually whenever we talk about an equation, we'll be talking about y equals f of x equals, let's say something like x squared plus 1. Let's say that's our function. That's what we've normally been working with. And let's say you plug in x equals 1 as your input, then you get an output of y equals 2. So that's what we've been working with so far. But this can only take us so far. So the example that we want to look at here, and let me use a different color, is what if we have a curve that looks something like this? Where we're traveling along this curve in a particular direction, right? So we're traveling from here all the way to here along this curve. And let's say we have a curve that looks like this. Well, notice we can't define this as y equals f of x because while A, it overlaps with itself, it doesn't pass the vertical line test. And B, we're trying to encode the information that you start here and you're going in one direction until you end up over there. Right, so that doesn't really work. So I'll say here that we can't define this as y equals f of x since this curve is not the curve of a single variable function. And the reason for that, as I said, is because it doesn't pass the vertical line test, so it can't be a curve defined by a single variable like y equals f of x. Okay, and another problem here, the other problem we're encountering here, is if we want something that describes the motion of the particle, then this motion happens over time, so we need to account for time. So another problem is that we need to describe the motion in terms of time. So that's our other issue here. Okay. So our solution here, so right here, solution to this problem is make x and y coordinate functions of time, and we can describe its motion with the equations x equals f of t and y equals g of t. Okay, so now we're just writing both coordinates as a function of time. And here we'll say that t is a parameter and we'll say here also that x equals f of t and y equals g of t are called parametric equations. And also I'll say, as t varies, the point x comma y, which is going to be equal to f of t comma g of t, varies, tracing out a curve. And we call this, so these are parametric equations, we call this a parametric curve. Right, so that's going to be called a parametric curve. And something important that I'll note here is that the parameter, remember the parameter was t, the parameter does not always represent time. And for example, the parameter could be theta, where theta represents the angle of some rotating object. Right. Okay, so let's go ahead and do an example here of what we mean when we're talking about these parametric equations. Okay, so example number 1 is going to say sketch the curve defined by the equations, and here we're going to have x equals t squared minus 2t and y equals t plus 1. Okay, so we've got two curves we've got two equations, two parametric equations. We're going to say that that traces out a curve. So let's go ahead and make a table so that we can try to figure out what this curve is going to look like. So I'm going to make a table of t, x, and y. So this is always going to work because you can just pick enough points, and if you just connect the dots, that's going to give you a curve. So I'll just pick some values of t. Let's go ahead and pick -2, -1, 0, 1, 2, 3, and 4. And then we just need to look at what the x and y values are going to be whenever these are the values of t. So we're going to start at t equals -2. And if we plug that into our equation for x, we're going to get that x is equal to 8 when t is equal to -2. And if we plug that into our equation for y, then we're going to get that y is -1 when t is equal to -2. And we just keep going like this. So we can actually fill out the whole table. So this is 3 and 0, then 0 and 1. So I encourage you to check these. But -1 and 2, 0 and 3, 3 and 4, and then 8 and 5. Okay, so now we just need to, well, now we have points, right? So for example, our first point would be 8, -1. This point would be -1, 2. And we just draw all the points and then we connect the dots. So that's our goal here. So let's do that. Let me be careful with my labeling here so that everything looks even. Right, so, and then up here I'm going to draw 1, 2, 3, 4, and 5. Okay. So let's just go ahead and plot our points. So we know our first point at t equals -2 is at 8, -1. So that's down here. So that's going to be our first point at t equals -2. Our next point at t equals -1 is 3, 0. So that's right here. Our next point is at 0, 1. So x coordinate is 0, y coordinate of 1. Our next point at t equals 1 is -1, 2. So that's up here. Then we keep drawing these. So at t equals 2, we've got 0, 3. So that would be up here. At t equals 3, we've got 3, 4. So we've got that here. And then at t equals 5, t equals 4, it's going to be 8, 5. So that's up here. Okay, and then we just need to connect the dots. So my drawing is maybe not the best, but you can kind of see what the shape should be here. And that looks kind of like a parabola. So we're going to get a parabola. And notice here, you start at t equals -2, t equals -1, t equals 0, t equals 1, t equals 2, t equals 3, and t equals 4. So those are values of t. And notice you start here, and you're moving as time passes along here. Right, so that's your direction of motion. So remember, these curves come with not only just the shape of the curve, but also the information about how you're moving as time passes. Okay, so let's go ahead and write. So let's call this graph 1. For example 1. And let me say here, another way to sketch right, so we're going to write another way to sketch, and the way to sketch it would be to write curve as x equals g of y, or y equals f of x. Right. So if we were to do that, so let me call this example 1.5. What we're doing here is getting rid of our dependence on t. So here what we're going to do is solve one of the equations for t. So solve for t. Because what we're trying to find here is x equals g of y. So we want to figure out what t is equal to, because we want x to only depend on y. So we know our equation was y equals t plus 1. They gave us that at the start, and we want to solve for t. So we can see here that t equals y minus 1. And then now our goal is to substitute into x equals t squared minus 2t. And then we substitute this value of t in, because then we're going to get a function for x that only depends on y. Right, so that's our goal. Solve one of the equations for t, and then plug that into the other equation. So if we do that, every time we see t here, we replace that with y minus 1. So if we do that, we're going to get x equals y minus 1 squared minus 2 times y minus 1. Right, and here you're going to have to FOIL that out, that first term. So if you do that, you're going to get x equals y squared minus 2y plus 1 minus 2y plus 2. Right, and if you go ahead and combine everything, you're going to get x equals y squared minus 4y plus 3. Right. So this is our equation for x in terms of y. And notice that's a parabola, but the parabola is in terms of y, meaning it's a parabola that's going to go open in the positive y direction, right? So the coefficient on y squared is positive, so it's going to open in the, sorry, what I meant to say is the positive x direction. That's what I meant to say. So I'll kind of fumble the words there, but let's draw what I meant. Here, this is opening in the positive x direction. So this, normally a parabola would open in the positive y direction, but since this is in terms of y, we've got to rotate it 90 degrees. And now this opens in the positive x direction. Right, so that gives us the information that this is what our curve looks like. So this method of solving for t allowed us to figure out actually exactly what our curve is equal to. And we have a name for this. Let me write that down here. We call this eliminating the parameter, right? Because we kind of just got rid of t. And I'll say here, importantly, there are disadvantages to eliminating the parameter. Since parametric equations tell us more information than normal functions. Right? So remember, in particular, so the first piece of information that a parametric equation tells us is exactly where the particle is at a given time. Right, so that's the first piece of information it gives us. And the second piece of information that it gives us is the direction of motion. Okay, so notice you're losing both of these things whenever you eliminate the parameter here, right? So these two graphs are the same, but notice, or so these two curves are the same, but notice these two equations gave us the information, the extra information about this curve, that this is exactly how the particle is moving with respect to time. We can just plug in a value of time to see exactly where the particle is at a given time. That's the first point here. And the second point here is that we know the direction at which it's moving. Here we don't know if it's going this way or this way. But for this, where we had the two parametric equations, we know exactly what the direction was. Okay. So as I said there, graph 1.5, I should have called this graph 1.5. Right, so graph 1.5 tells us where a particle has been, but not when it was at a particular point. It also can't tell us the direction of motion, but graph 1 tells us both of those things. Okay, and I'll say here, in example 1, there is no restriction on t, there's no restriction on t, so t can be any real number. Okay, so sometimes we restrict the parameter to some finite interval. And for example, so let's say we had x equals t squared minus 2t and y equals t plus 1. So notice those are the same as the equations we had up there, but we're going to add in the restriction that 0 is less than or equal to t is less than or equal to 4. So let's go ahead and look what this looks like. Well, if we drew it, then we know we're just having the part that starts at t equals 0 and ends at t equals 4. Right. So this is the part of the curve that we have. If we wanted to plot out the points that we had, this was at t equals 0, this was at t equals 1, this was at t equals 2, this was t equals 3, and this point was t equals 4. And we know that we're going along this direction, right? So that's the information that it gives us. So notice that's just part of the parabola starting here and ending here. And in general, the parametric, the curve with parametric equations x equals f of t and y equals g of t, where a is less than or equal to t is less than or equal to b, has the initial point. Well, you can kind of guess where the initial point would be. The initial point would be f of a comma g of a, right? Because you just plug in when t is equal to a. And terminal point, again, you can kind of guess what that would be. Here it would be f of b comma g of b. Right. So we just have names for those. Those are the initial and terminal points. And let's go ahead and do another example. Okay, so example number 2 is going to say what curve is represented by the parametric equations x equals cosine of t, y equals sine of t, where 0 is less than or equal to t is less than or equal to 2 pi. Okay, so that's our question here. And sometimes we have to look at the relationship between x and y. So here, observe that. So you might already be able to guess what this curve would be. But here, looking at the relationship between x and y, well, we know if we have x squared plus y squared, then let's write out what that is. That's cosine of t squared. So that's cosine squared of t plus sine squared of t. And remember what we said that was equal to? We said that's equal to 1. So we know x squared plus y squared is 1. Well, think back, what's that the equation of? That's the equation of a circle, right? And in particular, this is the equation of the unit circle, since this 1 is the radius squared, and 1 squared is 1. So the radius is 1, meaning it's the unit circle. Okay, so this is the equation of the unit circle that starts at, right, so remember what I said here, you plug in the left endpoint for t, you plug in t equals 0 into both of these to figure out the x and y coordinates at the start. Well, cosine of 0, that's 1, so it's going to start at 1 comma 0 because sine of 0 is 0, so that's going to be the initial point. And the ending point is going to be whenever we plug in 2 pi. So we plug in 2 pi here, so and ends at, well, if we plug in 2 pi, cosine of 2 pi is 1, and sine of 2 pi, that's 0. And you can notice, well, it's going to go around the circle exactly once, right? Because t is going between 0 and 2 pi. And if that's the case, well, it just goes around the circle once. And traces out the circle. So you can think about whether it would be clockwise or counterclockwise, but remember with our angles, as the angle increases, we're going counterclockwise. Remember, if you remember the unit circle, we're going counterclockwise as the angle increases. So traces out the circle in a counterclockwise direction. All right, so let's draw a graph of what's going on. So we know our equation is of a circle, and we know that we start at this point, and we're going to keep going around this way until we get back to the point that we started at. And that's exactly what the parametric curve would be. Okay, so let's look at the next example, which is closely related. So example 3, what curve is represented by x equals sine of 2t, y equals cosine of 2t, and 0 is less than or equal to t is less than or equal to 2 pi. So notice here there's two things that are different, not just one thing. So immediately it's obvious that the angles are different, right? Because the angles are now 2t instead of t. But also, it looks like we flipped around the sine and the cosine. So let's go ahead and double check. So again, we have, so let's try it again to do x squared plus y squared. Let's see what happens when we do that. Then we're going to get sine squared of 2t plus cosine squared of 2t, which, again, if you have sine squared of an angle plus cosine squared of an angle, we had the theorem we had the identity that said that this is 1. Right, so again, this is the unit circle because you have x squared plus y squared equals 1. So if we just care about x and y, it gives us the same thing. So again, this gives us the unit circle. But remember what I said is that the parametric curves encode more information than just the x and y. They also tell us about how the particle moves with respect to time. So we need to first look at the initial point. The initial point, right? So it gives us a circle, but the initial point is going to be, so we have to plug in t equals 0. So if we plug in t equals 0 here, then we're going to get sine of 0, which is 0. And if we plug in t equals 0 here, we're going to get 1. So actually now we're starting at a different place. We're going to start up here, right? Because that's the point 0, 1. And let's see what's happening here. Let's say we plug in t equals pi over 4. Then we're going to have the sine of, well, if we have 2 times pi over 4, that's pi over 2, which is going to be equal to, so sine of pi over 2. Just think back to the unit circle. The way I figure these out is always by looking at the unit circle. If we have pi over 2, that's this angle, and we look for the y value here, and we know this is a distance of 1 from the origin, so we know the y value here is 1. So the sine of that angle, because pi over 2 is 90 degrees, so the sine of this angle, y value here is going to be 1. So this is 1. And the cosine of pi over 2, again, we look for the x value here, and the x value is 0. So this is 0. So the point here, remember, the sine part is now going to be the x value, so the sine of this is 1. So it's 1, 0. So our second point on the curve, so we started here, and our second point is at 1, 0. So this was at t equals 0. This was t equals pi over 4. And now you can kind of guess that t equals pi over 2 is going to be the sine of pi and the cosine of pi, which if you look at the unit circle, it's the sine. So pi is 180 degrees, so you start here, you go to here. The sine of this, the y value, is 0. So this is 0. And then your cosine here, your x value is -1. So overall, that gives you the point 0, -1, which is here. Okay. So notice every pi over 4, you rotate a fourth of the circle. So if you rotate pi radians, which remember is just half of the total number of radians, if you rotate pi, you get back to where you started. Then if you rotate pi again, you get back to where you started again. So in reality, what's happening here is you're going to rotate once, and then you're going to rotate again. Right, so you start here, and then you rotate once to get here, and then you rotate again to get back here. So this is actually 2 revolutions around the circle. So as t increases from 0 to 2 pi, x comma y, which is equal to sine of 2t comma cosine of 2t, starts at 0, 1, and moves twice around the unit circle And again, we look at the direction in which this is happening. Well, remember, this was actually clockwise because we started here and we started going this way, which is clockwise. So it moves around the unit circle in a clockwise direction. Right, so just saying here, well, if we just looked at x and y, well, they give us the exact same things. These two examples, just looking at x and y, we just get the unit circle. But if you look at the parametric equations with the restrictions on the angles, they actually give us two different parametric curves. This is rotating once around the unit circle starting at this point. This is rotating twice around the unit circle starting at this point. This is rotating counterclockwise. This is rotating clockwise. So these are just different, fundamentally different parametric curves. Okay. So as I said here, different sets of parametric equations can represent the same curve. So let's say you just wanted a set of parametric equations to describe the unit circle. Well, this would have been a choice, but this would have also been a choice, right? So it's, let me maybe write this down. I'll actually write this down. So different sets of parametric equations can represent the same curve So it is important to distinguish between a curve, which is just a set of points, right, the x values and the y values, and a parametric curve which, as I said, is a set of points traced in a particular way. Okay, so let's say here, so we want to move on to the next example. I don't really know why I flipped that over if I'm going to have to erase it anyways, but let's move on to the next example. All right. So right here, before we start the next example, note in example 2 and 3, we eliminated the parameter by using a trigonometric identity in a similar way. We need to notice relationships between between x and y in order to eliminate t. Right. So our next example here is going to be where x equals e to the power of t and y equals e to the power of negative 2t. And as I said here, we're trying to look for a relationship between x and y. Well, notice if you raise this to the power of negative 2, you get this. So that's how they're related. If you raise x to the power of negative 2, that's equal to y. So, as I said here, y equals e to the negative 2t, which is e to the t to the power of negative 2, which we said e to the t was actually x. So it's x to the negative 2, which is the same thing as 1 over x squared. So y equals 1 over x squared. So that tells us the graph that we're looking at. That doesn't tell us the parametric curve, that just tells us the curve, just the shape of the graph. And I'll say here, because we already know how to graph this function, but I'll also say, but e to the t and e to the negative 2t are always positive, so we only get the first quadrant of y equals 1 over x squared. Remember, the first quadrant is just where both x and y are positive. So let's look at our graph. We know that our graph, we're only looking at the first quadrant, so we know the first quadrant looks kind of like this. And we need to establish what's the direction in which we're moving. So to establish a direction, we're going to plug in t equals 0 and t equals 1, just to see what happens when we move from t equals 0 to t equals 1. And whenever we do that, we're going to start here, and our next point is going to be over here. Our next point would be over here, and so on, if we just keep plugging in points. So we can see that we're moving from left to right. So we're moving this way. So this is actually our parametric curve. But remember, we started here at t equals 0. We didn't use anything before it, so actually we can erase this part. And we can say that this is actually our parametric curve. It follows the graph of 1 over x squared, but it starts at t equals 0. Remember, if you plug in t equals 0 here, you're going to get that both x and y are 1. So it starts at the point 1, 1, and it keeps going right along the graph of 1 over x squared. And that's our parametric curve. We've described both the shape of the curve and also the direction it's moving and how the points move with the passage of time. Okay, and let's write down one last example. Let's say we have x equals sine of t and y equals sine squared of t. And remember, we want to look for a relationship between x and y. So, well, we know that x is sine of t, so y is equal to x squared, right? So here, y equals sine of t squared, which we said sine of t is the same thing as x, so this is equal to x squared. So we have the parabola y equals x squared. Okay, and what I'll say here is But if we look at the x value, x is sine of t, we know that sine of t is always between -1 and 1. Right? So if sine of t is always between -1 and 1, then the x values are always between -1 and 1. So the point x comma y swings back and forth along the curve. And here I'll draw it. Curve would look like this. So we know we look like part of a parabola, but only the part between x equals 1 and -1. So this is our graph here. And we know that it swings from left to right. So I'll say we're going along this way, and then we're going along this way, and then we go back here and here. So it's just like a swing. It goes back and forth. And that's the information that we're given. So that's exactly what the parametric curve would be right there. Okay.